Okay.
I think it works.
I think it works. Okay, right. Sorry for a little delay, but next we have Ulrik Buchholtz to talk about synthetic locality theory. Go ahead.
Thank you very much, and thanks for the invitation opportunity to celebrate my team. Yes, I want to start with some memories. So I was also thinking about the same open problem when I first hear about my team and meet my team. And I think at first it was actually talked by Paolo at Ulrik, talking about selection, products of selection functions and that sort of thing. Very beautiful, and I was just struck by that. Of course, it's recurrent work. But I was like, okay, well, seeing someone I should also pay attention to, and then I subscribed to some mailing list, and so beginning to saw these beautiful messages on constructive views and ACTA, and I got interested in ACTA as well, even though I was doing proof theory at the time. I think the first time we met was in Bonn, and it's the first time I remember at the Hot workshop in 2016. Yeah, so I've been very inspired by both the Hot work, which was some first thing I came into after doing proof theory, and then more recently also coming back to the earlier work on constructive topology and topology domains and all the things following from Smith when you were younger. So this talk is about combining types and topology. Okay. So yes, synthetic mathematics. It's come up a few times already. So here's I like this quote by Hermann Weyl. It's written in one of his Nachlass papers, published posthumously. Large parts of modern mathematical research are based on a dexterous blending of axiomatic and constructive procedures. So axioms can sometimes be good, even though they might appear a little violent. In mathematics, we have the benefit that we're never actually destroying anything. We always have the opportunity to go back and look more carefully and smell and feel the sap. So, of course, the primordial example of this sort of story is this Euclidean geometry where you postulate. You have postulates, you have axioms about the postulates, you postulate that there are things, points and lines, and you have various axioms about how they relate to each other, and then you make constructions based on those. And Russell said that this has the benefits of theft over honest toil, and I think this is where the constructivity comes in, because you pay for what you stole, you can really see it, because at some point you construct a model for your postulates and your axioms. Okay, but there are, of course, many more modern examples. So I just put a list here, I'll go through all of them. I mean, one of the most famous ones is the story about synthetic differential geometry, where you create a topos where you have a smooth real line and all the functions there are infinitely differentiable. And you have some kind of axioms, more the axioms of this, but one of the key ones is that if you take this little algebra where you take polynomials mod out by x squared, that's exactly the function size spectrum, so the subset of R of square zero elements. And then you can do the same thing in algebraic geometry. There's seen a big revival, also following work of Blechschmidt, which I'll also mention later. And of course, there's computability theory, domain theory. I should have put on the citation with lingering idea as well. I put in one of them. And something I've also been working on, ongoing collaboration with Danny Gratzer and Jonathan Weinberger, is about synthetic higher category theory. So this is also a synthetic approach. You work very much like in John's talk with a distributed lattice, and the most basic case, you assume that it's totally ordered. In the more refined version, you just look at the local objects for the forcing condition that says that the interval is totally ordered, and then you can do higher category theory just in type theory, and all you have to know is that arrows compose, and then you get a fixed simplification of the theory of infinity one categories. And so the most recent work, which you should look forward to, is that we now have a construction of the infinity one category of infinity one categories, and from there on you can do a lot. You basically go off to the races. I think also from a logical point of view, this work on synthetic stone duality is also quite interesting. But there are lots of other examples: real cohesion, measure theory, probability theory. Alex is here, and stuff I haven't mentioned. So that's all very nice. We have all these toposes. We work out what happens in the internal logic. We make it. We make a topos that satisfies something that we would like to do. We can do type theory in there, and we can add whatever we figure out is true in these models as postulates, axioms, and acta. And then what happens if you want to go back and say, okay, now I want to externalize. I proved something about manifolds, infinite differential manifolds in synthetic differential geometry. Now I want to do some measure theory on these manifolds as well, and combine measure theory with the infinite differentiability. Or I want to do higher category theory, and I also want to do real cohesion. And you want to do several steps of these. And maybe one day we'd also like to do this in a proof system. So we have to come up with a language that allows us to do this. Of course, you could do this analytically again and say, okay, I'm going to prove that I'm going to define type theory and type theory and prove that all these things are models analytically, and then you work with these results that you have models. But this somehow is against the spirit of synthetic mathematics. So let's talk about a vision, which doesn't quite exist, but I think it's something that several people share, and I put on some of the approaches here. And I'm sure there are others who thought of similar ideas, but here are some things. So Taishi Omura wrote a series of it's like a little online webbook on synthetic topos theory, which goes in this direction. And Buchholtz and Sadler presented a types, a generalized logical framework, which is not quite about all toposes, but about GATs, and that already covers a large range of theories. The generalized algebraic theories, not all geometric theories necessarily. And then at the Topos Institute, there's ongoing work. They think about it in terms of modeling, of doing their CAP collab work, which is having a workbench for creating modeling systems and then interpreting their models. But it's very related to this program as well, particularly so Owen Lynch has this idea of element model type theory, which I'll come back to in a few slides, and David S. Myers, together with Mitchell Riley, think about theory type theory, and they've worked out some beautiful some parts of the story. So what I'm going to talk about right now is this more pedestrian approach, which you can do right now. So the whole picture is like getting a whole new type theory. But we want to be a little bit more modest to begin with and see what can we actually do today in ACTA. And so that's going to be the synthetic locale theory, which is joint work with Shifrin Manes and Martin Williams somewhere else.
Ulrik, so what I called geometric type theory, does that live on there somewhere, or is it different?
There's also some work on arithmetic universes I'll mention at the end, and but I think you like to not have any non-geometric. You want to just purely geometric. Yeah. Here I want to have my cake and eat it too. Okay. I want to have my universes and my infinitary inductive types and my pi types. I want to freely use them, and I want to then think about what is geometric about it at the end, and maybe I can prove something is geometric. So feel free to interrupt, but there are lots of connections that are that I could mention here. Okay, so another way of stating what we want after is having synthetic mathematics eat itself. You can do a synthetic mathematics of synthetic mathematics, and what would that even mean? So this picture is something that Ulrik Buchholtz likes to use. The credit is Karina Wilbold. So we want to go between the internal and the external. So it's very nice that we can make these internal languages and things look beautiful there, but it's good to talk to someone outside, not just be in your own little bubble all the time. So maybe we can postulate, doing synthetic approach, postulate that we have theories and they have models, and give new axioms that will allow us to derive what are the internal statements true over a particular theory, the topos given by a theory. So maybe the intended model of this would be something like the multiverse of all toposes, which is a constructive generalization of the multiverse of sets theories that, from the point of view of classical set theory, all you have are these transitive models of set of C, but from a constructive point of view, we have many more larger multiverse. There are more things between heaven and earth. But we'd like to make distinctions between the all the maps and the Italian maps, corresponding to the arbitrary constructions that we would like to have. So some of us would like to have, like infinitary type universes and pi type and so on, and the geometric things that are preserved by whole bag on all maps. So these are some things like sigma, identity types, and finitary hierarchical types. So that's the division. Okay. So what are some challenges that the endpoint have to accompany? So let me just come back to this idea of Owen's of element model type theory. So here they're coming in different order, but it is we try to make a type theory that has at least 4 kinds of judgments. So X is the topos, little x is the point of that topos, A is an Ital map, and little a is a section of it. And in another language, this dictionary, you can say you have theories and models, and you have types and elements. If you rearrange this, you get element model type theory. Okay, so you would also need to have modalities, and they have to be sort of local modalities. You have a bunch of modalities that connect how everything fits together. And that's something that you can get at a little bit with an idea of Mike Schulman's called the codexification. Because the typical way we do multimodal type theory, you need every modality to have a further left adjoint, but you don't have that in general for maps for the compositions of geometric morphisms. But you can sort of universally add them, but it's still going to be a complicated business that the final story will have to contend with. Some other challenges is that the intended model is, of course, not a model type theory, so you can't even just like say, I have a model type theory, let's start to figure out what happens in it. And it's not even a good category anyway. It's not remotely small because the type of maps is too large. So think about maps from, say, a topos into the topos given by a theory T. They're supposed to be models of T in the sheaves on X. So these are completely unbounded. So if the theory is a theory of rings, then you can have rings of any size. So the usual strategy would be to kind of use a universe hierarchy. So you can think about, okay, what are categories in vision stratified types? So that's another challenge that the final story will have to continue. Okay, so now let's come back to what we're proposing for synthetic locale theory. So we start at the first 4. We start this with propositional theories. They're better understood than general theories. And small ones. So we fix an external universe hierarchy and only look at theories in V0 and the maps between them in V0. So the reason, if you're not predicatively minded, you may say, well, in the propositional case, the smallest problem goes away because there's only a set of models of a propositional theory anyway. But I think it's an important methodological point, which I think Martin will appreciate, that working predicatively can help you prepare for a more general situation. So working out this story without assuming any predicativity will help us for the wider program. Okay, so this gives us a good site we can manage, and has a nice topology given by the covers the axes given for each individual theory. And that helps a little bit that that's locally V0 small. So there be one many covers, but if you fix the codomain, then there are only V0 many things. That's basically proof theory. Write down the type of proof search trees given by the axioms, and if your theory is small, then there are only, if you have some infinitary inductive types in the meta theory, that's a small collection of proofs again.
Sorry, what were you saying the topology was again?
So you give yourself a new locale for every base open, and then if you have some, do we have a marker?
There should be markers on the boards.
Marker on the board. So if you have something like a conjunction of atoms is that there's big disjunction of some other conjunction of atoms, then these guys will give objects that cover this. So the usual thing, but you can lift it to localities by taking by going global. By adding, you take T and then add as an axiom the PJ is the conjunction of these. These will have maps to T added with the conjunction of the PIs. And then you take P. And then because theory interpretations, the maps will be theory interpretations, so this will satisfy the axioms for coverage. Because if you have an interpretation of S and T, then you will be able to again get a proof tree that capture these.
I'll have to think about it a bit, but
Yeah.
thanks.
Okay. So now you have a small site that we can actually make into an infinity topos if you like and get a model of hot. So this will now have a universe hierarchy where we drop the bottom universe because we only had a V1 small site. But that's nice enough. It's still an infinite hierarchy of universes. And we're going to need to have the crisp spatial type theory to talk about global elements. And we can't use the new version of doing this, which is multimodal type theory, because that's the thing where you need to have left adjoints, but there's no left adjoint to the locally constant sheaves. However, the old style version of doing spatial type theory does work in this setting. So luckily we can use the split context calculus, not the locks calculus, which is useful in many modalities. Okay, so then we do have some remnants of the bottom-most universe. So there's let's call U0 the locally constant sheaf of V0 small things. And let's say S0 is going to be your nade of Sierpinski. You can also have higher versions of Sierpinski. But they're not closed under, these universes are not closed under all constructions, they're only closed under geometric constructions, so that's fine. And then this S0 does have a kind of algebraic structure, is a distributed lattice with U0 small soups, supremers. Okay. So what I think we proved is not published yet, so take it maybe with a grain of salt. So in this model internally, for any U0 small theory, geometric theory, there's a quotient inductive type giving an S0 algebra of the same kind, so distributed lattice with a distributed lattice map from S0 that preserves U0 small soups. Such that the evaluation gives a nice model, so the same kind of reality axiom that we saw for the Cockburn axiom and synthetic algebraic geometry and synthetic domain theory and so on. So this is the starting point. So that's how far we've gotten. Still need to then actually do some synthetic locale theory, so it's still just work in progress. However, it's important to know that we can recover the non-geometric constructions on the étale, on the open propositions, using CRISP. So there's always a map from one large étale families to the arbitrary étale proposition to the arbitrary sub things. But there's only a map after you take global elements, so that's why you have to relativize this to a crisp theory T that doesn't depend on any further parameters. Then you can take the interior, so you get a kind of relative adjunction. And right now, I think we're postulating this as one. We can think about whether it could be defined. There are lots of things that's still to be worked out. Okay, that's the basic idea. Right. Then I'm just going to go to the outlook. So the immediate next step is to actually prove some theorems of topology, maybe some of Martin's theorem. Maybe we can prove that Cantor space is searchable or something like that. Then we would like to derive this quasi-coherent deduction into reality, which is work in progress. I didn't put it up because we haven't proved it. I would have put collections quasi-coherent deduction, but I gave a reference to a blog post in the Topos Institute website from David S. Myers, and then you can read about it. then we're going to finish the paper, of course, and start formalizing some things in ACTA, build ACTA flat. And then okay, then the further steps later on would be to go higher, to do in one autolysis, some of the 0-1, and go larger to allow larger theories and larger maps between theories. That's where things get quite complicated. And then there's this thing about one person's external is another person's internal, and the way we have it, we always have to go back to the base. And so, okay, if you want to iterate things, you have to figure out, well, what does the composite looks like from the starting point. That's not the ideal situation. I think we would like to be able to work more locally and not be so brutal. And that might require some ideas of theories eating themselves. So that happens already in some known cases, but I don't quite know how to write a type theory for it. So gaps eat themselves, arithmetic universes eat themselves, locally presentable categories eat themselves in a way. Yeah, and another point is that this synthetic locality doesn't look very much like the analytic one because we don't use presentability in this one. We just have something that should be regular cardinals is a small thing. So that's another challenge. Maybe we can bridge that gap. And then, of course, you want to have natural type theory that you can compute with, or put it in Zinn for Torsten, because it's not type theory if you can't normalize. So it's still only work in progress until you have that. Okay. This quick. Happy birthday.
Thank you. Questions?
Just minor suggestion and a question. Can you go back to your own list of suggestions?
Yeah.
So you say maybe Cantor space is searchable, but maybe all stone locales.
Yeah.
And the question is, so when doing non-synthetic, so analytic local theory in hot with Iberg.
Yeah.
So one obstacle to being predicative, which you mentioned, was that there isn't a terminal locale in absolute terms, because the type of propositions is different in all universes.
Exactly. Yeah.
And so how are you dealing with this in your synthetic approach?
Well, that's what I'm saying. We're not doing that really. We're not doing the completely right thing. We're only looking at the small things, the small maps. So we don't see the real issue that you mentioned there. So that's it's a pro and a con. So we actually do have a point in that sense, but we don't really have this idea of that the universe can, the size of theories can grow without bound. Right. Paul?
Could you pass the mic?
A little warning about locales versus spaces. So you can take T0 topological spaces and embed them in a Cartesian closed category with Scott's equidological spaces construction. Right now, this doesn't really work for locales. Well, if you try and do it, I've forgotten the name of the guy who did it now. You get a class size structure.
Yeah.
And you can put that in more basic terms. It comes from the unpleasant behaviour of the rationals with the Euclidean topology, right? And the effect of this is that products don't preserve epies. So this is a bad starting point if you're looking for Cartesian closed categories or something like that. So just a little warning about local theory.
Yeah, I think that's very related to the fact that you don't have this further left adjoint to the locally constant sheaves on locales, right? Because there's a whole topic called shape theory. So what you get is what happens in this codex-duplication as well. You get a pro-homotopy type or a pro-set. And maybe that has to be part of the picture as well. And that's related to this nasty spaces like rationals with the Euclidean topology.